Welcome back, guys. This is Ashwin here. In this video we're going to see about speech emotion recognition system. So we already created one project with the help of LSTM. We have predicted the emotions from the audio of a person speaking. So based on that we will predict the emotions from it. We got around 67% validation accuracy, but it is not the best one, as we have created a basic LSTM model to predict the classes. So this is a advanced version or the next version of that project. So we are going to use transformer and pre-trained models to do the classification, as these models have seen so many audio samples and they can clearly understand between the emotions and the context that the audio data have. So what I'm going to do is I am not going to code everything from scratch. As you can see here, some of the code cells are very similar to that project. If you didn't see that first project, you can see at least half of the video, at least the data exploration side. You can click on the right top corner of this video to see that. Now on this part, I'll just explain the overview of the code, and the new code I will type it myself, and we will walk through together. Okay, now these are the same import modules which I have used before. So the Librosa library will be used for loading audio files, and the additional import files which I have been used is this torch modules and Wav2Vec model along with the trainer arguments. So this will be help in the process of building the model pipeline and training it. Now let's run this. Make sure you set it to GPU, so we will train the model very quickly with the help of the GPU, and then we will load the dataset. I already created the notebook from the dataset. As you can see, this is the dataset. So we are loading it here. I have added this path, like once we reached 2800 it will break, because it has some additional audio files which is repeated, which caused some issues in the previous video. So that's why we are using this to stop the process, to avoid that replicated files. So in total we have around 2800 audio files. If more data was there, we could train a RNN or LSTM from scratch and it would provide better results, but 2800 might be minimal for an LSTM model. So let's run these things, and you can see the full path of the audio file, and these are some of the labels, and we have created a data frame out of it, and for each class label we have around 400 samples in place, and these are some exploratory data analysis. So all the classes have a uniform distribution, so there is no class imbalancement. If there is class imbalancement, you can replicate some of the audio files and make the class reasonably balanced, at least to avoid overfitting on a specific class. And then this will plot a wave plot like this, the audio visualization of the audio file, and this will give you a spectrogram of the audio file. And for each emotion I have displayed it how the audio will be, and you can also listen to the audio.
Say the word home.
So like that you can listen to the audio file. Let's run this as well, and I think many of you guys have some issues in the Librosa library while plotting this wave plot. So that is also updated here. You just have to use wave show because of the latest module update. And let's run these things, and for all the classes we'll just take one audio file and display it. So these are all the audio files, and you can explore it here. It will just show you the full audio file, and you can see the pictures.
Say the word good.
Now these are the exploratory data analysis. Again, if you want a detailed explanation, you can always refer my previous video. Now let's start the new part. We have to go create a dataset class, create custom dataset class. As we are using PyTorch, we pretty much use any custom class to get the input and the corresponding output in the formatted manner. Now first convert labels to integers. Label map equals label colon index for index label in enumerate of df of labels of unique. I'm just creating a dictionary map of the string label to an integer. So this will create the dictionary, and again we can have the inverse map. So when we get the integer as output from the model, we can use this inverse map to get the actual string of the class. So inverse label map equals, we have to do the same for label comma index in label map dot items. As we already created a dictionary, we can reuse it. And finally we will format the labels. So df of labels dot map of label map. Let's just display the first two rows of the data after conversion. Now you can see before it was a string, now it's an integer, so it's easier for us to process. Then we will create the custom class audio dataset or instead of having more generic, speech emotion dataset. So this will be more customized. Def, we will have a constructor, self, pass the data frame, processor. We have to initialize some processor for doing a pre-process of the audio file, and max length of the audio file. I'll have 16,000, which is like a sample rate. Now self.df equals df self.processor equals processor, and then finally self.max length equals max length. Okay, we have done some initialization, and we will override the length method. And again, if you are not going to use length mains, you can always ignore this, but it's a best practice to do that. So when you have like len of train dataset object, it will give you the whole dataset length, which is self of df, whichever the df we are passing it here, and def get item. When you are using an index to get an item, it will call this function self and index. Now we will get the audio path from the data frame. So self.df.ilog of index of audio paths, and correspondingly we have to get the label. Now we got both audio path and label. Load the audio file. So speech comma underscore, which is the sample rate. Torch audio also have this function. You can also use Librosa here. So load audio path and speech equals speech dot squeeze dot numpy. Now we have loaded the audio and converted to a numpy variable. We have to pad or truncate the audio file. As you can see, there are different lengths of audio file from 1 second to 5 seconds. So we have to pad or truncate the speech to the required length. Pad or truncate the speech to the required length. Now for example, we just have to see what is the maximum length. Maybe in this case, if we just get the length of the data, it would show us, because it has like 2 seconds. Maybe we could have 2 seconds as the max length. Just in case, we will check this. Okay, I think the emotions we have converted to here. Maybe let's have a actual number. I think fear will be 0, 0, 1. This we can have it as 2, so 2 would be fine. Let's see it. So you can see the length of the audio file, and we will also see the sampling rate. The sampling rate is 22,050, and based on this we will have a maximum of 2 seconds. So what we could do is sampling rate multiplies by 2. So this will be our max length here. So all the audio files will be processed up to 2 seconds based on the sampling rate. And we can comment this. If you want, you can uncomment and check with other audio files as well. Maybe I will keep it down here. Now let's resume our process. If len of speech greater than self dot max length. That means if it goes beyond 2 seconds, we will truncate it. So speech equals speech of colon self dot max length. Else, that means if the speech is less than the max length, means we have to pad it with zeros. So for that, speech equals np dot pad of speech. We will pad it with zeros. So 0 comma how many times that you want to do the padding, that will be self dot max length minus the length of the speech. So the remaining value will be the padded items. So let's say you have audio length of 20,000 and we have 44,000, means it will pad the remaining 24,000 values with zeros. And finally we will have constant, so constant padding. Now this is done. Pre-process the audio file. Now inputs equals self dot processor of speech sampling rate equals, I think it's 22,050, right? So 22,050 based on the sampling rate we got. And then return tensors equals PyTorch padding equals true, and here also we will have truncate equals true, and max length will be the max length of this self dot max length. And I think this will get me the sample rate. We could pass it here. Now this is done. Finally, we will squeeze the inputs. So input values equals inputs dot input values dot squeeze and return input values, pass the values, and labels. We have to convert it to PyTorch format or tensor. So torch dot tensor of label, and d type will be torch dot long. Okay, just in case I'll just print this SR just to double check whether it is getting the sample rate, or do we have to do any other further processing. Let's run this. Now split the data for train and test. So for this I'm going to use scikit-learn. Scikit-learn dot model selection, import train test split. Now train df and test df equals train test split. Okay, it's not suggesting. Pass the data frame, test size equals 0.2, which is 20%, and random state will be 42. Okay, let's run this. Now we will initialize the processor. We didn't initialize it before. Initialize the processor and model. Processor equals, that is Wav2Vec2 processor dot from pre-trained of Facebook slash Wav2Vec2 base. So this is the smaller version of the model, and this is trained by Facebook, and we will load the model in a similar way. Wav2Vec2 model. I think we need Wav2Vec2 for sequence classification from pre-trained of pass the model, which is the same as here, and then number of labels. We have 5 labels in total, so pass the number of labels here. Let's run this. So for the first time it will just download all the model and their weights, and after this we will load the dataset. Train dataset equals speech emotion dataset of train df and the processor which we have loaded. I think that would be enough, and we do the same for test dataset. This will be test df and processor. Let's run this once, and as I said, I have to do the testing. Dataset of 0. So it's giving me some error about label, which means the key is missing. So this is labels. So labels, let's run this once and check it again. Okay, the sample rate is keep on changing, so we have to define a fixed sample rate here. As I said, my suspicion is correct. It is getting the sample rate, but we can fix it. So because of this model which is trained on 16,000 sample rate, we have to resample this. So resample the audio file because of the different frequencies. We'll do speech equals torch audio dot functional dot resample of the audio file, original frequency which is the SR, and new frequency we will set it here 16,000, and based on this I will just change this to 32,000, and everything will remain the same as it is. Let's run this and check this again. Okay, here we have to pass 16,000 as that is the new frequency. Okay, now you can see the input values and the corresponding label, and this is the extracted or processed audio file. Now this is done. We will create data loaders. Now train data loader equals data loader of train dataset, batch size. This is a pretty big model, so I will have 8 and shuffle equals true. Now we do the same for test data loader of test dataset, batch size 8 and shuffle equals false. Okay, now the dataset is created. Here we will set up training parameters. Set training parameters or set training arguments, and here we will import additional modules here. Before that I will set the training arguments of output directory. I will have it in results, then evaluation strategy, it will be epoch, save strategy. If you want to save the model on the best validation loss or accuracy, you can do this based on epochs or a specific number of steps, and learning rate which is 2e power minus 5 per device. Train batch size I will have it as 16. Okay, I think we also defined the data loaders. I don't think we need the data loaders in this case. Can delete it. Per device eval batch size I will also pass this as 16, and then train epochs will be 3. Why we are training for only 3 epochs? Because this is a pre-trained model, and if we train for more epochs means we might lose the original trained information. We don't want to do that, so that's why we are training it with very less learning rate and only for few epochs. And report 2, just have it as empty, or else you will face some wang db for logging purpose. So this is the training arguments, and after that create function for computing metrics. Now from scikit-learn dot metrics import accuracy score precision recall f score support, and that's all we need. Let's define the function compute metrics. Even PyTorch has all these modules. I'm familiar with the scikit-learn, that's why I'm using this. You can use any module that you want. Everything has the same formula. Labels equals spread dot label IDs. This will give you the ID or integer, and spreads equals np dot argmax of spread dot predictions. So this is the original labels. I will have it here, original label, and this would be the predicted label. I will have access equals 1, model predicted labels, then accuracy equals accuracy score of the original labels and the prediction labels. Then we do the same for precision recall f1. Support is nothing but the number of samples. We don't need that. So precision recall f score support of labels, spreads, and average equals weighted. So this will give you the weighted average, and return accuracy precision. So by customizing the custom compute metrics, we will have all these metrics while doing the training. If you don't do this, means you will only get the training loss and validation loss. So accuracy, precision, recall, and f1 score. Now we have defined the compute metrics. Next we will initialize the trainer. This is nothing but like a fit module which you used for TensorFlow. So trainer, or else for PyTorch you have to write a very long snippet for the custom training loop. This will be a straightforward trainer where you can just pass the model and arguments and complete the training very quickly. Pass the model, arguments will be the training arguments, and train dataset equals train dataset, eval dataset, which is the test dataset, and finally compute metrics, which is the function we have defined. Okay, now this is done. We can start the training. So trainer dot train. So before going further, I have tried to train the model, but it's not actually using the GPU. It's just loading the model, and it is not using the GPU at all. I think because of some model version mismatch or some problem in Torch audio. So we have to fix that, and this would be weighted. So please update that. And in the speech emotion dataset, we are loading the audio file using torch audio and resampling it and changing to numpy array. So instead of this function, we can use speech sr equals librosa dot load the audio path. So this will just directly load the audio, and you can also specify the sample rate here. So SR equals 16,000. So this will resample it and it will give you the speech array, and you can do the rest of the processing as it is. Now let's try to rerun this, and you can see the size, which is the max size we have set. And let's also run these things. Now you can see the training has started instantly, and we are just 2 minutes away, and the GPU is fully utilizing. Before that it was just loaded to memory, and only the CPU was utilizing, and it was very slow. So this is the better approach. Now after the training is done, we have to do the evaluation. So results equals trainer dot evaluate. So this will just use the evaluation data set, and it will give you the results. So we can view the results here. And if we want to use test data set for testing, so I will have test predictions. Now we will get the data set by index. So I can get a random index here. So index equals test data set. I think we can use a random function. So import random, and random dot rand range 0 comma len of test data set. So this will give you a index, and from this we will try to get the label and print it as original label. So print original label, just to see whether we are correct or not. So we will get the index, and from test data set of index of, we have to get the label. Let me just check whether it has a plural form. Okay, this is its labels, and this will give you the label of it. And let's see, I think if it's a tensor means we can change it. And now we will get the input of this label. So input values equals test dataset of index of input values dot unsqueeze of 0. I will move this to CUDA, then with torch dot nograd. So this is for doing the test prediction or getting the outputs or prediction from the model. So outputs equals model of input values, and we will get the logits equals output dot logits. Then from that we will get the predicted class equals logits dot argmax of dimension equals -1 of item. We can just display the predicted class. I just need to check whether this is running perfectly. Now you can see the training is done, and we got around 99.8% accuracy. So that is good, and you can see how the training loss is decreased gradually for the validation loss, and even the F1 score, all the other metrics have been improved. Let's do the evaluation. and you could see uh, the same results. At least in the third epoch, we are almost getting the same results. So this will be the final evaluation accuracy. Let's do the test prediction. Okay, this is outputs, and this is coming it as tensor. I can have it as integer. Okay, now you can see the original label and the predicted class from it. Now we don't want to see the label as integers, we want to know what the actual class is. So we will have inverse label map of this, and for the predicted class we will have predicted label, and we will use the inverse label map of predicted class. Run this. Now you can see, so this is discussed, and we will repeat the same here, and this is happy. As this got around 99% accuracy, pretty much all the samples will be correctly labeled. And if you want to test out your own data set, you just need to pre-process it the same way which we did. So you just have to load the audio path as it is, and you have to do until this point and take this input values and unsqueeze it and use it in CUDA, or you can just ignore the squeezing part and use it directly as it is. So that's how you can use a real-time test sample to do the prediction from the model. And that's pretty much it, guys. So some parts might not work if you make like small errors, or there may be some module adjustments that may happen in different version. So be sure to use specific versions for the end-to-end project if you want to replicate it. So that's all I have. If you like this video, hit the like button, and if you have any queries regarding this video, leave a comment below, and I will see you guys in the next video.